Hey everybody, welcome to Neutron Stars and Black Holes. Sadly, hey, this is the last chapter in Unit 3 on the stars. Geez, this all is a sad moment, but we're going to go out with a bang because neutron stars and black holes are some of the most bizarre objects in the entire universe. What I've got pictured here, by the way, is a black hole sitting in the center of a galaxy. This is kind of a tease for the next unit where we talk about galaxies and cosmology and where supermassive black holes do lurk in the centers of galaxies. So let's dive in here. Intro to neutron stars. Okay, neutron stars are, remember we talked about this before, one of the products of a supernova explosion. What basically happens is you have electrons that get jammed into protons and they become neutrons. Those are particles without any charge. So the minus of the electron, the plus of the proton are neutralized in a neutron, which is a very bizarre object. Plus a neutrino. This is an object that has very low mass, travels at nearly the speed of light, but most importantly, is extremely elusive. These things can travel through light years of lead, theoretically, and not even notice it. And they're the ones that, remember, escape in 2.5 seconds from the core of the sun, whereas regular photons take hundreds of thousands of years. So these things are associated with supernova explosions, and believe it or not, neutrinos have actually been observed coming off supernova explosions. So this theory is very attractive. Anyway, neutron degenerate matter is the greatest, most dense, and the strongest material in the universe, about 10 to the 15th power. That's the density relative to water, 1 followed by 15 zeros. That's a billion times almost the density of a white dwarf. We were talking about how dense those things were. And this is basically the density of the nucleus. So you don't get anything bigger and badder, nastier than this. Neutron stars that form at the core of the supernova explosion, when they survive, they're always less than 3 solar masses, and they're small. Generally, they're only about 10 kilometers in diameter, but that can vary. The reason this number is solid, greater than 3 solar masses does not occur, is because if you piled up more neutrons than 3 solar masses, it would collapse the entire star into a black hole. In other words, it would be unstable. Just too much, in other words, the weight of the neutron star, if it's above 3 solar masses, could not be supported by the strength of the neutrons. Okay. Now, stars that begin life between 8 and 20 solar masses will go supernova. We've talked about that. In fact, even bigger ones will go supernova, but the smaller ones are the ones that leave behind a neutron star. Now, the upper number is fuzzy. That means this number is not well known. It may be 21. It may be 21 and a half. We don't know yet. Now, pulsars are taken as observational confirmation of the existence of neutron stars because they're assumed they are spinning neutron stars. They spin from with periods of a millisecond to a few seconds. You should read page 230. There's a beautiful graphic in the text that talks about the so-called lighthouse model and this is, see, neutron stars beep, and they beep from, as I mentioned, from every millisecond to a few seconds. And this explains how a spinning pulsar can produce that kind of radiation. So check that out. These things are known all over the place. There are a couple of thousand of them that are known. There's probably many more than that actually in the galaxy. The weird thing, are you ready for a weird thing? Pulsars sometimes have planets. Now that should be, initially that sounds crazy because pulsars are neutron stars. Neutron stars are the remains of a gigantic explosion. Remember that sometimes outshines the entire galaxy. So the original planets, if there were any around the star, must have been destroyed, but people think that maybe the planets we see around pulsars were captured at a later time or a result of some object that was torn apart as it went by the pulsar. The universe is a strange place, friends, trust me. Now, intro to black holes. As if neutron stars are not bizarre enough, black holes are the strangest objects probably in the universe. They have escape velocities greater than the speed of light. And what that means is that an escape velocity is simply how fast you have to go to get out of somebody's gravity field. Like if you're on the Earth, how fast do you have to go to leave? 25,000 miles an hour. Okay, and that's why we need big rockets today to do that. However, an escape velocity for a black hole is greater than the speed of light, which is 186,000 miles per second. Okay, so with something like that, that means not even light can escape, and neither can you. Okay. Now, the feeling is that, although we don't know, this is another fuzzy number, if the mass of the original object is greater than 25 solar masses, that's what MS stands for, the core collapse cannot be stopped. Remember, we talked about the core, the entire star collapsing into the core because it runs out of the silicon burns into iron, and the iron cannot burn, and so it's like creating ice cubes in the center of the star. However, a singularity forms. In other words, space-time is warped, and this is the core of the black hole, a so-called singularity. A singularity is a we don't know exactly what a singularity is because it's something that apparently does not obey our laws of physics. Tut tut. It's a very sad thing, but we don't know exactly how they work. We know that they seem to be objects with zero volume and infinite density. That's why people are concerned about what exactly that means. The so-called Schwarzschild radius, named after a famous physicist, is given right here. And let's see, 2 and g are constants. C is the speed of light squared. So the radius really depends on the mass of the material inside the black hole. Black holes really don't care much about what comes in. They're mainly concerned about things like this. They want to know how much, they don't care if it's a Volkswagen or a chocolate cake that comes in to the event horizon. All they care about is how much did the Volkswagen weigh, how much mass was there, was there any electric charge on the chocolate cake, were either of them spinning, and that's it. And mostly they're concerned about mass. And so the more mass the black hole has, the bigger the Schwarzschild radius. Now the location of the event horizon surrounds the singularity. That's what the Schwarzschild radius is. The event horizon is a real boundary. It's a boundary between our universe, the one that you and I live in, and the inside of the black hole. Now you should be, well, I'll show you in a minute. The inside of a black hole is totally speculative, even though it's based on mathematical theories. Time dilation. Usually this occurs near an event horizon due to warping of space-time by the black hole. That means your clocks appear to be slowing down. You'll see what I mean in a minute. Now here's a black hole model. The only thing we know for sure about this is that there is an event horizon, which is the boundary between our universe out here and whatever is in here. We think that all black holes have some sort of a singularity. If the black hole was spinning before it became a black hole, there'll be a ring singularity. If it's not spinning, which is probably very unlikely, there'll be a point singularity. Point singularities mean instant destruction, and ring singularities open the possibility of wormholes, and I'll tell you about that in a minute. This one is spinning, so we have a ring singularity, we have an event horizon, there's an inner horizon and an outer horizon. Remember, this is mathematically based. There is no observation to really confirm this. It's likely to be a long time before we know for sure what's inside a black hole, because if anybody's ever gone in one, they haven't come back to tell us about it. That's the problem. Now, I thought it would be fun to think about what would it be like to go into a black hole. Well, first of all, this is a party. We're going to have fun, and so you'd invite your friends, in addition to the people that are traveling, your colleagues who are traveling with you in the spacecraft. So your friends are watching you in the spacecraft approach the event horizon, and they see your clock slowing down. So they're frantically, they haven't had this class, so they don't know what time dilation is. They're frantically radioing you saying, hey, your clocks are slowing down, silly. But you don't see anything like that. And your friends continue to see your clocks slow down until they finally stop when you hit the event horizon. And you also stop too. You freeze there, and for all eternity, your clocks stop, and you will appear, the residual image of you will appear on the edge of the event horizon to your friends on the outside. That's what relativity is about. What you see in the universe depends a lot on what your position is. If you're outside, if you're back with your friends far from the event horizon, you see one set of things. If you're inside the spacecraft, you see something quite differently. However, and here's an example, you inside the spacecraft notice no time dilation effects, and you pop through the event horizon like it wasn't there. Whereas your friends think that your clock stopped and you're stuck on the outside of the event horizon. And eventually they'll read about relativity and know that that's not really what happened. Inside the event horizon, now this is where everything gets speculative because nobody's ever been there and reported back, but our theories show that inside the event horizon, our universe disappears. In other words, the universe that you and I live in now will no longer be visible. Sorry. And you're going to be headed toward, and by the way, the escape velocity is greater than the speed of light, so you're committed. You're not getting out. Now, you're also forced to head for the singularity. It'll either be a point or a ring, as I pointed out before. A ring is what you'll probably see, and if you steer into the plane of the ring, not the edge, you can, under certain circumstances, engage a wormhole. This is a portal to space warps, which means traveling great distances in zero time. That's called a space warp. Zero time, not just small times, or possible time travel. So it's all right here for you. Time travel is potentially a problem because, for example, if you go into the past, which would be fun, because you'd be the smartest person around, you'd also know a lot of things that were going to happen. But the trouble is, if you do anything that changes the future, particularly the future relating to you, you could become non-existent. And this is a famous paradox. And if you've ever seen the Back to the Future movies, and almost everybody has, these things keep coming up. And it's really true. Change the past and you change your existence potentially. But some people even think that time travel to the past is probably impossible. I think it's probably possible, but it's different than people expect. If you go into the future, the game is wide open. The only trouble with going into the future is it's going to be hard for you to get a job because everybody's going to be smarter than you are. They'll all have bigger computers. They'll all know about more physics than you do. You won't be very marketable, and so you'll probably wind up in the pokey or something. So you have to be real careful about traveling into the future, even though I think it'd be a lot of fun. If time travel into the past is possible, you're going to be the boss because you'll be the one with the biggest computer. You'll know everything that's going to happen if you're smart, and you can basically take over, but it's dangerous, as I mentioned before. So that's your introduction to black holes and a little bit of relativity thrown in. We're going to finish this chapter by talking about gamma ray bursts, which are real. They're observed in other galaxies, generally a few hundred per year, sort of like an average of one a day. And gamma radiation, by the way, is the hardest, most dangerous radiation there is. The gamma ray bursts are the brightest electromagnetic events in the universe. That means in terms of electromagnetic radiation, like light radiation, X-rays, microwaves, and gamma rays, these are the brightest events in the universe. Okay? Now, they last from 10 milliseconds to hours. Remember, these are seen in other galaxies only. The model, which is still speculative, is that you have a very massive star. Remember, these things are associated with black holes eventually, that runs on a nuclear fuel and does what all big, massive stars do when they get hungry. They collapse. This one collapses along the rotation axis directly into a black hole. There's no explosion. The gravity is so intense that the poor star can't even blow up. And it just becomes a black hole. And along the way, it gives off this burst of gamma ray radiation, and it's a beamed radiation burst. That means it's like a gun. It has directionality. If this thing is pointing at you, that's bad news. Now, some people have suggested this could be a problem for Earth, the gamma rays probably wouldn't get to the surface of the Earth, but the ultraviolet rays could. And this would dramatically, potentially harm photosynthesis and DNA, including yours and mine. Some people even think that if there was a gamma ray burst that was pointed at you, even from another galaxy, that could cause mass extinction events on the Earth. Now, I doubt that, but still, it's speculative, and we really don't know, first of all, how these things work. We do know they exist, but we don't know really what they mean for the Earth. Probably not as anything as dramatic as extinction events.